It means that you need to know the condition. So if it is a conditional branch, the condition has to be known, whether you are going to branch if 0, whether you are going to branch if it is whatever the case might be. So they give it, the machine language instruction has got codes for the branch. Now, what you see there, CCC, those are the conditions, or those are the codes for the conditions. We can branch if 0, we can branch if negative, like, and so on. So there you have got the conditions on the screen. You can see that condition. Someone can say branch if the result is not 0. So the condition for not 0 is given as 0, 0, 0. That is the condition code. Branch if the result is 0. So that is the 001 is the condition for if 0. Branch if there is no carry. Branch if there is a carry, and so on. Now, these conditions, you are not supposed to cram them. They will be given in case they are needed. But whenever you branch, like I said, that you can branch to another part of memory, and you go and run a function, and then you return it to the main program. So if you are branching, it means that you have to specify the address where you are branching it to. That memory location where, for example, the function is found in memory. So you have to give the address where you are branching it to. So this one is also a 3-byte instruction where you have the operation code is the first 2 bits and then the last 3 bits. That is the operation code. Then we have got the condition codes, which are the middle 3 bits, and then the address where you are branching it to, the lower part of the address, and then the upper part of the address. Okay. Now, I think we can continue from there. So this one is a machine language instruction which says branch if 0. So we saw that the condition code for if 0 is 001. So that one becomes the machine language instruction for branching if 0. Okay. Now let us continue addressing modes. You are hearing me? Addressing modes. Is everybody hearing me?
Yes, sir, we can hear you properly.
Okay, okay. Now we define addressing modes as the methods we use to locate and fetch an operand either from an internal CPU register or from a memory location, either from an internal CPU register or from a memory location. Now, what we mean here, if I can give you examples, if you can have somewhere to write, can you write for me these 3 statements? Someone can say 3 plus, okay, 3 plus 5, or let me rephrase it, x is equal to 3 plus 5. So if you can write that statement there, x is equal to 3 plus 5. And then someone else can say that x is equal to b plus c. B plus c. And then he goes ahead to tell you that B and C are registers. Register B has a 3, and the register C has a 5. Okay. Then you have someone who says X is equal to P plus Q. And he says that P is a memory location. P is a variable. It is a memory location which is holding a 3. And the Q is a memory location which is holding a what? A 5. So if you examine those 3 statements, the first one Okay. I was giving an example that if you want to understand the addressing modes, I gave these 3 examples. I said that you can write down x is equal to 3 plus 5. Then I said that you can also write down that x okay. I said that you can also write down that x is equal to b plus c. And I said that b is a register which is having a 3, and c is a register which is having a 5. And then someone else can say x is equal to p plus q, where p and q are variables. That means their memory locations, where memory location p is holding a 3, and the memory location q is holding a 5. Now, when you look at those 3 statements, you realize that you are all doing the same thing. It is just a matter of adding 3 and 5. But the difference is where is the 3 and where is the 5. In the first case, the 3 and the 5 are given immediately in the instruction. The instruction itself is the one which has got the 3 and the 5. So we can say that information is available immediately. Then in the second example, we are adding b plus c. Register b has got a 3 and register c has got a 5. So in your cases, your x will be 8. But this time, the operands are in registers. So you have to find out first what is in register B, and then you find out what is in register C. Okay? Then in the third case, it is the same thing, but the only difference is that what you have there in the instruction are addresses, or in other words, they are memory locations, where memory location P is holding a 3, and the memory location Q is holding a 5. So addressing modes, like we know, when we talk about address is finding out where a certain entity is. For example, if I can tell you, if I can say that my address, if I can tell you my address, it means I'm telling you where I am found. Okay? So addressing modes are meant to tell us where the operands are. So in those 3 cases, the first one, the operands are found within the instruction itself. The second case, the operands are found within the registers. And the third case, the operands are memory locations. They are found in memory. So addressing modes, they are the methods which are used to find where the operands are, and then bring them to the CPU in order to perform an arithmetic operation. So they locate where the operands are, and we fetch them and bring them to the CPU to perform an arithmetic operation. So in those 3 examples, the first one is called the immediate addressing. So the first example where I am saying that x is equal to 3 plus 5, that is the immediate addressing, which means that the operands are in memory. Sorry, the operands are within the instruction itself. You find they are immediately within the instruction. So here we define immediate addressing as that addressing mode where the information is in the instruction. Here information is the data you need. The data you need is given in the instruction. When you say x is equal to 3 plus 5, so whatever you need is there within the instruction. So that is immediate addressing. Okay. On the other hand, we have the second addressing mode, or let me talk about the third address, the third first, where the operands are in memory. So what you see are just the addresses of those memory locations. P is an address and the Q is also an address. So the instruction gives only the addresses. The real operands are in memory. So this type of addressing is called direct addressing. So in direct addressing, the operand are addresses. So what you have in the instruction are addresses. So that's what I mean there when I said that direct addressing, the address is a part of the instruction, which means that it is the address which is given in the instruction, but the real operands are in memory. And then the third addressing mode there is what we call register addressing. So this one is what I explained like in my second example there, where I gave an example and I said that X is equal to B. Okay, I'm sorry about that interruption. The network is quite poor this morning, but I was talking about the addressing modes, and I said that these are methods which we use to find and locate where the operands are. We find the operands and then we bring them to the CPU. So the third addressing mode is register addressing. In register addressing, what you have in the instruction are names of the registers, all addresses of the registers, but the real operands are in memory. So in register addressing, the operand is in the register, okay? And the register's address is what is given in the instruction. So like I said that if I say X is equal to B plus C, the 3, which is the operand, is in register B, and then the 5 is in register C. So the operands are in registers, but the instruction gives us only the codes, all the names of the registers. So that is register addressing, okay? Then we have indirect addressing. Indirect addressing, here we are saying that the address is in a location, the address is in a location whose address is specified as a part of the instruction. So this location, it may be a register, which we call a register indirect addressing, or it may be a memory location. So if I can give an example, you can say that you have register B, you can write it down, that register B has got a 10. In register B, you have got a 10. And then you have a certain memory location whose address is 10. Whose address is 10, and maybe that memory location has got a 5. Okay? So if we are talking about indirect addressing, we will mention a register B, but the contents of register B, which is a 10, is not the value which we need. Okay? So the value in register B is an address to a memory location. So you go to memory and you find a memory location whose address is 10, and you find what is stored in that memory location. So if that is a 5, then you can pick that 5 as the required operand. So that one is indirect addressing. Okay. So we also have base addressing. Now, in base addressing, it is somehow like indirect addressing, but in base addressing, there is usually what they call the base address. The base address. So the base address can be a register, or it can be a memory location. So they give you a number, like let me say register B is our base. And if register B has got a 10, and then what we need is a memory location, let me say whose address is 15. So that means that you take the 10 and there is a number which you add to the base. That number is called a displacement. So you take the base value and then to that base, you add a number which we call a displacement, and then you go to the required memory location. So here you have got a base, and then you add a displacement, and then you get to the right memory location, which has got the needed value. So that one is called the base addressing, okay? Then we also have what we call index addressing. So we usually indexing is like incrementing. Okay, someone wants me to repeat the example again. I wish you can tell me which example, because I have so far talked about immediate addressing. I talked about register addressing. I talked about direct addressing. I talked about base addressing and the index addressing. So I don't know which exactly what you want me to repeat. Base addressing, okay. So I said that in base addressing, there is usually a number which is given, and that number is called the base value, okay? And then they also give you another number which you call a displacement. So if you want to locate a memory location where your operand is, you take the base value, and to that base value, you add a displacement. So it is base plus displacement. Then that takes you to the required memory location. So that is what we mean there when we say that the required address is calculated by adding contents of a memory location or register called a base to a number called a displacement. So these two, the base and the displacement, are the ones which are given in the instruction. But to find the actual memory location where you are going to pick data from, we call that one, sorry, we calculate by taking the base and adding a displacement. So that takes us to the required memory location. I hope that is clear now. Then index addressing is usually a process of incrementing and decrementing. In C, for example, we usually talk about C++, I++, okay? Or I subtract. That means you are incrementing. That means you are incrementing by 1. So that is what we call indexing. So someone can say that you are indexing a certain value. That means you go on adding a 1 to that value until you get to the required memory location. So that one is called indexing. So you go on incrementing by a given value, or you go on decrementing by a given value. Okay? Okay. Now, assembler language instruction, assembler language, okay? So remember, we have been talking about machine language. Machine language is a language which uses only zeros and ones, like those examples we have considered. But machine assembler language is another type of language which is closer to machine language. Okay, so the only difference between machine language and assembler language is that assembler language uses abbreviations instead of using zeros and ones. So it uses abbreviations which can be understood by a human being instead of using zeros and ones. But whatever you do in a machine language, there is a corresponding statement in assembler language. So that is the similarity. For every statement in the assembler, there is a corresponding statement in machine language. Okay, so that is the only difference. But otherwise, whatever is done in machine language is what you also do in the assembler language. Only that in the assembler you use abbreviations. So we have got a software which we call an assembler. An assembler is a software which converts assembler language to machine language. Okay. Now, in the assembler language, we have got two types of instruction, two types of statements. We have got two types of statements in the assembler language. There are some statements which we call instructions. There are statements which we call instructions. Now, the instructions are the ones which are translated to machine code. And then we have other statements which we call directives. So the directives are not translated into machine language directly, but they just give us, they guide us on how we are going to translate to machine language. Okay, so those two are the different types of statements used in the assembler. A statement can be an instruction or it can be a directive. Remember, an instruction is converted directly into machine language, whereas a directive just gives the directions, but it is not the one which is translated. Now, I have said that the assembler language uses abbreviations for the machine language instruction. So the abbreviations are called mnemonics. Those abbreviations, we call them mnemonics, okay? And then the character strings are the ones which stand for the instructions themselves. So let us look at this example. Let us look at this example. Someone who can give that example, he says that the answer is equal to x plus y. I think that is something like a C language statement. Answer is equal to x plus y. Now, what does that mean? It means that there is a memory location x in memory, which has got a certain value. And there is also a memory location y in memory, which also has got a certain value. Now let us assume that x is a memory location and it has got, let me say, a 6, okay? And the y is a memory location which has, let me say, got a 4. So if I say that the answer is equal to x plus y, it means that you go to memory, find a memory location whose address is x, okay? Pick whatever is that memory location. So in this case, I said that it has got a 6, and bring that 6 to the CPU, because you are going to add, and addition is done in the CPU. Then again, you go back to memory, you find a memory location y, pick what is in the memory location y. In my example, it is a 4, and bring that one also into what? Into the CPU. Then the CPU will add the 6 and the 4, you get an answer. And then the answer will be taken into memory and it will be stored in a memory location called the answer. Okay, so if you are to break that one down into machine language instruction, you remember we said that we have to fetch what is in memory and bring it into the accumulator. So the first instruction there is saying load the accumulator with the X. That means go to memory, find what is in memory location X and put it into the accumulator. You remember the instruction to load the accumulator from memory. You remember it was a 3-byte instruction. Okay. Now, whatever we fetch from memory, we have to use that statement, load the accumulator. And whatever we pick from memory, it comes to the what? To the accumulator. Now, when I pick X and I bring it into the accumulator, I need also to go back to memory and pick Y. Now, when I bring Y into the accumulator, what is in Y can overwrite what is in the accumulator, which I fetched first. So if you don't want your X to be overwritten, you can put it first into a register before fetching the second operand. So that is why we are saying that you do a register to register transfer, and you move what is in register A to register B. Okay, then you can now load your register A, which is the accumulator, with Y. Okay, and then you add what is in the accumulator to what is in register B, and then we store what is in the accumulator to memory location answer. So there you can see that whatever we did in machine language instruction is described by those abbreviations. So the first instruction is load the accumulator with the X, move what is in A to B, then load the accumulator with the Y, then you add what is in the accumulator to what is in register B, and then you store what is in the accumulator to memory location answer. So you can see that that simple statement there, which is written as the answer equals the X plus Y in a high level language, it is broken down into 5 steps in machine language or assembler language. So for every statement in the assembler, there is a corresponding statement in a machine, and the reverse is also true. For every statement in a machine, there is also a corresponding statement in the assembler. Okay, so that simple example where you are adding X plus Y and putting the answer in the memory location answer, it is broken down into 5 machine language instructions. And since for every machine language instruction, there is a corresponding assembler language instruction, so we have also 5 assembler language instructions. So remember, in the assembler, we use abbreviations or mnemonics. That is what we call them. So there, LODA means load the accumulator. Move is the register to register transfer. So here we are moving A to register B. Remember, even in the machine language instruction, register to register transfer, you remember we begin with the 0, 1. Then we do what? We mention the destination register, and then lastly, we mention the source register. So that's why we do the same thing also. That is how we do the same thing in the assembler language. You move what is in register A to register B. A is the source, Okay. So you load the accumulator with the X, you move what is in register A to register B, then you load the accumulator with the Y, add the B. You remember, even in machine language instruction, adding, remember, we are usually adding it to the accumulator. So we only mention one register, the source register. The other register is the accumulator. So when I say add B, it means I am adding A to what is in B. And then the answer is always in A, the accumulator. So the last instruction is storing what is in the accumulator to us. Okay? So that is an example of a machine, an assembler language instruction. Okay. Now, what is the format of an assembler language instruction? Assembler language instruction, the format is given above there. Usually there is a mnemonic, which is the abbreviation for the instruction. And then we have the operand. We can have one operand, or we can have two operands. Like in the previous example, when we say load the accumulator with the X, LODA is the mnemonic and the X is the operand, okay? Then move BA, MOV is the abbreviation, all the mnemonic for moving, that means the register transfer. The operands are registers, they are register B and register A. Okay, so usually for any machine language for any assembler language instruction, there is a mnemonic, and then you can have one operand or you can have two operands. And then if you want, you can document your program by putting their remarks. So if you are going to document your program, you put that semicolon and then you write your remarks. It means that the assembler will not bother itself by looking at the remarks when you put that semicolon. Some instructions have got a label. So labels are usually used if you, for example, you are going to perform a branch where you can say that branch 2, and then you give a label. For example, you can say branch 2 mark. So marker is a label where you want to branch to it. Maybe it is a memory location where you want to branch. So some instructions begin with the label, but a label is not a must, because some instructions might not be branching instructions where you don't have labels. So ideally, the format of one is an assembler language format, of an assembler language instruction. We begin with the label, which is optional, okay? Then from the label, we have the mnemonic, which is the abbreviation for the instruction. And then we have got the operands. The operands can be 2 or it can be 1, okay? You need to know the difference between the format of an assembler language and the format of a machine language. Okay? Can someone remind me the format of a machine language? The format of a machine language. Can someone let me know the format of a machine language? Remind me rather. Hello? Can someone just let me know the format of a machine language instruction? Nobody remembers? Hello, are you there? Okay, it is the opcode and then the operands. We have an opcode and then the operands. That is very good. It is not opcode and the instruction. It is the opcode and operand. So for every machine language instruction, there has to be an opcode and there have to be operands. Again, the operand can be one or you can have two operands. Now for an assembler language instruction, we can have a label, then we have a mnemonic, and then the operands, okay? So these are some examples of assembler language instructions. Someone who can say branch address, move A, comma, M. So branch address, that BRADDR, is a label. So you can see that after the label, you have a semicolon, then you have a mnemonic, then you can have two operands, like in that case, a destination operand and a source operand, okay? Like you can have a register transfer where you can begin with the label now, because so in that case, the label is now, okay? The mnemonic is move, MOV, then you mention the destination register and then the source register. So that is how assembler language instructions look like. A label, but we are saying labels are optional. They may be there, they may not be there, but at least the mnemonic has to be there. The mnemonic has to be there, okay? And then the operand. So that is another example. When you say LDA num, load the accumulator from memory location in num. So the mnemonic is LDA, that is the mnemonic. And then the operand is the memory location where we are picking the data, which we are transferring to the accumulator, okay? Then there is that example where we say move immediate E6. Remember, in moving immediate data, we said it is equivalent to someone telling you to put a number into a register. So this is like someone telling you to put a 6 into register A. So we say move immediate 6E. So you mention the mnemonic, then the destination register, and then the immediate data which you are moving. Okay. So that one is also an example of what? That is an example of an assembler language instruction. Then we have this one, jump if not 0. So the mnemonic is jump, that is J. J means jump. So that is the mnemonic. Then there is the condition not 0, jump if not 0, okay? And then you mention the what? The operand, which is an address here. So jump if not 0 to a memory location here. So if not 0, you will have to branch to a memory location called here, okay? So those are instructions. Now remember, we said that in assembler language instruction, we have got two types of statements. You can have an instruction, or you can have a directive. You can have an instruction, or you could have a directive. Now remember, we said that instructions are those statements which are usually converted directly into machine language, okay? While the directives, they are not converted into machine language, but they just give us a direction. So that one is the format of a directive. It can also begin with the label, which we are saying is optional, but then there has to be a mnemonic, and then it also has the operands. Okay. So this is an example of the Intel 885 directives. Okay. So one of the directives is called define storage, and we abbreviate it as DS. DS means define storage. Okay. Now, what does it do? It reserves the memory and assigns a label to the first byte of the reserved area. Now, for me, I can compare that DS to a declaration in a high-level language. When I say, for example, in a high-level language, if I say int x, can someone tell me what that means? Int x. If I say in a high-level language, let me say C, and I say int x, what does that mean? Can someone let me know what that statement means? Hello? I'm waiting. Can someone tell me in a high-level language, we usually say int x. So what does that mean? What are you telling the operating system to do for you when you say int x?
We are saying that x is an integer.
Can someone maybe explain it better than that? If I say int x, what are you telling the operating system to do? Okay, so some people are writing that you are telling the operating system you're telling the compiler to gazette 4 bytes in memory of a numeric value. Okay, someone is saying that to allocate memory, very good, okay? So when I say int x, I am telling the compiler to go to memory, okay? Gazette, or in other words, reserve some space where you are going to put integers, or where you are going to put an integer, and you label it x. Okay, so it means that you are reserving. When you reserve, maybe you put a label there to indicate that this space has been reserved. Okay, so when you say int x, you are telling the compiler to go to memory, find the memory location, reserve it, and put there a label x. So it means that after some time, maybe you will put there an integer value. Okay, so sometime you can come down and say x is equal to 3. So this means that you are putting a value 3 into the reserved memory location. So int x is reserving space, or in other words, reserving memory. So it is the same thing when I say define storage. I am reserving memory, okay? And I am putting there a label to that reserved area. So when I say, for example, like you can see on my screen, if I write and I say array DS20, it means go to memory, reserve 20 memory locations, and put a value, put a label array. reserve 20 memory locations and put there what? A label array. Okay. And that label is usually put on the first byte of those reserved 20 memory locations. So that one is the first directive. DS means define storage. It reserves the memory and then assign a label to the first byte of the reserved area. Okay. So in for example, array DS20, it means reserve 20 bytes of memory and assign a label and put a label array to the first byte of those reserved memory locations. Is that okay? Is it fine? Hello? Is that fine? Yeah, okay. Then the second directive is called define byte, and we are calling it DB. DB means define byte. Now, define byte is the same thing as declaring a declaration. You see, in a high-level language, we have an assignment. When I say int x, that means that I am assigning a variable x, okay? Then when I declare, it means I am declaring what the value which is in the memory location which was assigned the x. So if I say x is equal to 3, I think that is a what? A declaration. So this is putting a number or a value into the assigned memory location. Okay. So like in a high level language, when I say int x, it means I am just reserving space and I am labeling it x. But when I come down and I say x is equal to 3, then it means that I am putting a 3 into the reserved space. Okay. So it is used to put values. Define byte is to put values into a pre-assigned values into the memory location which were previously done what? Which were previously reserved. So there is an example. If I say that num define byte and I say 14, that h just means a hexadecimal value. That 14 is a hexadecimal number. Then I have a string there of characters ABC, and then I have another binary number. The B stands for binary, okay? So if I write that, it means I am putting values. If I say DB, define byte, that means put values into those memory locations. So that is how memory will look like. When I say num, DB14, ABC, blah, blah. So the first byte, I will put a 14, a hexadecimal number. Then those 3 characters, ABC, that is a character string. We know in memory, characters are stored using their ASCII values. So the ASCII value for A is a 41, then B is a 42, C is a 43, and then the last binary number, if you write also in hexadecimal, it is a 68. 0110 is a 68. So if I give that directive num db 14h, ABC, 0110. So this is how memory is going to look like after that directive. So it means that those memory locations will be assigning the values, they will be given values. Okay? Is that fine? Fine? Okay. Someone is saying not really, and another one is saying yes. Okay. If I can repeat, we have those two directives. The first one was define storage, and then the second one was define byte. Let me use an example. Suppose I write num ds2, and then someone says num dd2. The first one is num ds2. Then the second one is num db2. So num is a memory location, okay? So when I said ds2, define storage, so this means that reserve to memory location, okay? So define storage, you remember we said that it is reserving storage. So you are reserving 2 bytes. So when you say num ds2, you are reserving 2 bytes. Now you put a label num on the first byte. Again, when I say that num db2, it means that put a number 2 into the reserved memory locations. Is that right? Okay. Now, in this example, it seems it is confusing some people. I'm saying that if I say num db, db means I'm going to put values into memory location. And then I said db14h, it means h is just standing for hexadecimal number. You remember when we are talking about memory, in memory, numbers have to be in binary. So either, but when writing, we can write using hexadecimal. Okay, so here I am saying to make matters easier, you can write 104, which means 104 is a hexadecimal number, so it is 1 byte. Then the characters ABC. Remember I said that A, B, C are characters. We all know that a character takes 1 byte. A character takes 1 byte, but in memory, you can't write A. In memory, you can't write A. So character A, if you want to find its value in memory as a string, you have to convert that one to its ASCII value. Now, the ASCII value for A is a 41. The ASCII value for B is a 42. And the ASCII value for C is a 43. Someone is saying he didn't understand how we get 68. 68 is that last operand, 0110, 1000. I said that is B binary, but we usually use hexadecimal when writing into memory. We know they are binary numbers, but we convert that one to hexadecimal. So 0110 is a 6, 1000 is an 8. So we get 68, okay? Someone is saying that you thought hexadecimal values are from A10 up to F, which is 15. Now confused of H being hexadecimal. H is just a label. Like I can say 14, I can put a D, which means that that is a decimal number. That is a base 10 number. So 104 can be a base 10 number. 104 can be a hexadecimal number. So in order not to confuse whether it is a base 10 or whether it is a hexadecimal, that's why they put that H there to mean hexadecimal. Okay? Then this is just, H just means the hexadecimal. It is just a label, like you can see the last operand, I put a B, which means that it is a binary number, okay? Hello, hello. I'm sorry I had muted. I'm sorry about that. So another directive, we have got 3 directives. Another directive is define word. Define word. Remember the first one was define storage, DS, and that one was just reserving. Then the second one was define byte. That was putting values into the memory locations. Then this one is define word. Now define word, according to the Intel 880 people, the Intel 885, a word is 2 bytes. Remember, the smallest storage is a bit. Then we have a byte. Then 2 bytes can be called a word. Okay? So if you say define word, it means this time those operands which are given are words, which means they are, each one is 2 bytes. It is an operand which is 2 bytes, and you are going to put those 2 bytes in memory. So there is an example there. If I say define word, task 1, task 2, 092AH, it means that task 1 is going to be 2 bytes. Task 2 is also going to be 2 bytes. And then the last one is obvious, because if you have 092A, those are 4 hexadecimal digits, which means 16 bits. 16 bits, those are 2 bytes. That one is obvious. Now here they are telling us that let us assume that task 1 and task 2 are addresses. Remember, we said that addresses of Intel 885, each address is 2 bytes. So if task 1, for example, is an address which is 2010, and the task 2 is also an address which is 1080C, and we are going to load those ones into memory. Define word is loading values into memory. So on the first byte, where we have the label table, we put task 1, which is 2010. But like we are writing, we first write the lower part of the address first, and then the upper part next. So if it is 2010, the lower part is 10. That is what we write first, followed by the upper part, which is 20. Okay, so that is task 1. Task 2 is 1080C. So the lower part is 80C. We write that one first. Then 10 is the upper part. We write that one next. Okay. Then the other one is those 2 bytes, 092A hexadecimal. So that one means the 2A is the lower part and the 09 is the upper part. Okay. So that one is the define word. The define word is also putting values into memory locations, but this time the operands are not single bytes, but they are words. In other words, each operand is 2 bytes. Is that also understood? Okay, okay. So I'm sorry we have been in this. How did they get 10 for dy? I explained that task 1, we are assuming that task 1 is an address which is 2010. Okay. And then task 2 is an address which is 1080C. So if we are loading 2010 into memory, we put the lower part of the address first. The lower part is 10. 2010, those are 2 bytes. If they are hexadecimal digits, each digit is 4 bits. You remember when you convert to hexadecimal, every hexadecimal digit is 4 bits. So if I have 10 hexadecimal digits, those are 16 bits, which means 2 bytes. So the lower part, the first byte, we put a 10. The second byte, we put a 20. And it is the same thing with the 1080C. The lower part, you put 80C. Then the second part, you put 10. Okay? Someone was asking what happens to H. I said the H is just a label, meaning it is a hexadecimal number. So the number is just 092A. Yeah? It is not part of the number. H is just telling us 092A is a hexadecimal number. Like the previous example where we had a B. In this example, we put a B, which means 011010000 is a binary number. So if we are loading it into the memory, we put it into hexadecimal, which is 68. Okay. Any other question? So if there is no other question, I think we can stop here. I'm sorry the connection was not very good today, and we'll pick it from there. Is it Thursday or Friday? Whatever, I hope I will be there. But then I requested for an extra lecture. Remember last week we missed a lecture, and I told you, I requested that you can give me an alternative day when we can have this lecture, but you didn't get back to me. So it means that we are lagging a bit behind, and I would request that we have an extra lecture. So that I leave that for you to discuss amongst yourselves and let me know. I sent these slides to the class rep. He can distribute them to you. I sent them on his email. The class rep has the slides for this chapter 1. Okay. Which topics are missing? Someone is saying some topics are missing. I don't know which topics are missing. Maybe someone will have to explain. Because I just sent only one to the class rep. The slides I sent to the class rep. Okay, so if someone has got a problem, maybe, yes, I will upload it to Moere. I will upload, but I haven't got that time yet, but I will upload, don't worry. But meanwhile, before uploading, that's why I decided to send this, at least the first chapter 1 to the class rep so that you can share. Okay. Yeah, certainly I will upload them on Moira. You don't have to bother about that. Okay, so if there are no more questions, I just wish you a nice day. Thanks. Well, I think we can meet next time. Okay. Have a nice day.